So one location is the J20 header, which is right above. This is the header just above the LCD, and you can connect the ultra cap between pins 1, which is the square box, and pin 2 on that actually. So yeah, this is pin 1, which is ground, and this is pin 2, which can be connected to the positive terminal. This is pin 4. Oh, sorry, pin 4. So pin 1 for ground and pin 4 for the ultra cap, and you can either directly connect it from the top or use the bottom side over here. Just make sure you have the right configuration. The right one is pin 1, and the fourth one is right here. So so you can also so you'll also have to remove one of the resistors here. Is that for removing the debug module? Okay.
Removing the resistors are for something else.
Okay, but okay, just pin 2 should be grounded though.
You can pull pin 2 to, yeah, so you ground pin 2 in order to put the debug
Yes.
microcontroller into reset.
Okay, yes. So that was another optimization. So what you could do is connect pin 2 to ground either directly or have a jumper. So, but you want to keep in mind that when you do that, that'll disable the debugger. So when you want to debug or flash the code again, you'll have to disconnect that wire to enable the debugger again. And you can also connect the cap to J17, which is located here.
Right to the top by the USB.
The J19. Okay, right here. So you can connect it. Yeah, that's the power supply, the alternative power supply that you can use to cover the board. And so you can plug in the ultra cap at that position also. At the plus 5, the positive lead, and ground for negative lead. But in this case, you'll need to short the diode because it's a one-way. If you have the USB plugged in, that won't allow the ultra cap to power the board, and you do need to short out the D5 diode. That is when you want to charge the ultra cap. So the diode is located. D5 is right here. This is the diode right next to U22, and you short that out when you want to charge the ultra cap. Another way to connect the ultra cap is at position 1 of J14 application header, which is this, and as you can see the numbers. So this is J14, and you can connect the ultra cap to pin 1 for the positive terminal, and
Actually, no, you keep the ultra cap up at that connector at the top. Here you're just connecting a wire from the 5E in to the 5V0.
oh, okay. So I'm sorry, I'll repeat that. So you can leave the ultra cap connected to this top end right here, and connect the 5V in to V out on J14. That will also serve the purpose. Okay. Is there any questions about project 461 specs? Then you can move on to 561 part. Is that clear? Alright, so now we'll look at how we can integrate the SFPS demonstration code to the Project 3 code that you have, and how you can analyze that part of the code. Okay, so the basic idea here is that you have a buck converter and you want to drive the buck converter using the PWM signals from the board and then monitor the voltage at the output of the buck converter and display it on the LCD and also display the reference voltage that you have set for the buck converter to operate at and also use a dial to display that voltage on the LCD. And again, so the buck converter, the way it is operating is it has two loads. One is a fixed load, one is a switching load. The fixed load is it's already on. Both the loads are already on the board, but the switching load comes into the circuit through a MOSFET, which is externally connected between. So the MOSFET is present on the board and can be connected to the buck converter in series with the switching load, which will enable the switching of the load. So the idea is so the control loop to control the buck converter is taking too much time in the demonstration code, and you're supposed to reduce the execution time of that so that you can synchronize it with the PWM signal. And that way you allow the voltage regulation to work more efficiently and with a faster response time. So your aim is to reduce the execution time to 6.8 microseconds, and I'll demonstrate how you can monitor the execution time and sort of profile the code as you go on optimizing it. Okay, so the PWM signal is generated using a timer module, which is TAU10, and how that works is you initialize the timer with a certain period that you want the PWM frequency to be set to, and have that channel would have that timer will have two channels. One is the master channel, one is the slave channel. So as I mentioned in the previous lecture, the master channel will be responsible for the frequency of the PWM, and the slave channel will be responsible for the duty cycle. And I'll explain how you can initialize the timer in your Project 3 code to set up the PWM signal as an output from the board. And when, so at every positive edge of the PWM, the timer will generate an interrupt, which is given by the TM. This is basically an overview of the software that is existing in the demonstration code, and you're supposed to implement the same thing on the Project 3 code, and I'll explain how you can carry that over. So the timer will generate an interrupt, which is the TM10 ISR, and that interrupt will trigger the switching load by turning on the GPIO or turning on the MOSFET, which is in series with the switching load. And alongside, this will also trigger the ADC, one-shot ADC conversion. So when the ADC conversion is complete, then it'll generate an ADC ISR, and you'll call this function, which will determine if it is time to update the duty cycle or if there are any changes. If it's time to update the duty cycle based on a counter value. So right now, since the PWM signal runs at every 20 microseconds, your execution time in the demonstration code for the control loop is around 45 microseconds, which is why you cannot run the control loop every switching cycle of the PWM. And in order to, so that is why you have that delay. So every time a positive edge occurs, you check if it is time for the control loop to run or not. If it is, then you run it. Otherwise, you skip and wait till the next one. And so first, I'll show you how we can actually look at the waveform being generated by the buck converter and the basic characteristics. Oh, before going into that, I'll also discuss how the buck converter is connected to the board. I skip that, but so if you look closely, there's a connector right here on the top left of the converter, and it has various inputs. The first one is the gate drive, which is the input for the PWM, and right here the first one. And you can insert the wire either ways. But if you look closely, there's an arrow on top of it, which is not visible in this. But if you look very closely, there's an arrow on top of the connector, which points to the direction where you should be inserting the wire from. That'll make a neater, or it'll make a form connection. But if you do plan to insert the wire from the other side, it will work, but it might be a loose connection. So you just make sure that the wires are intact and it is properly connected. So anyway, the first point is the gate drive, which is the input of the PWM signal. The next pin is the VSense, which is sensing the output voltage and sending it to the ADC. So it is divided by a potential divider because the ADC cannot go above 3.3 volt reference, and you're using the since the voltage input to the ADC cannot go above 3.3, so the input voltage has to be scaled down in order for the ADC to sense it. That is why you use this voltage instead of the Vout. And then you have the actual Vout generated by the buck converter, which is a third pin. And you can use this pin to monitor the actual voltage on a square or a multimeter, which is also, so VSense is sensed by the ADC and scaled up using the formula and displayed on the LCD or the dial. And Vout is the actual voltage being produced by the buck converter, which you can monitor in real time. And then you have the power, which is, then you have the switching resistor. I'll remove this wire to show you the connection. Then you have the switching resistor right here. So this needs to come in series with the MOSFET. And the way the connection is laid out is, so you have, okay, so you have a buck converter, and you have a Vout, you have a ground, so this is positive, negative, and then you have a load, which is a fixed load, R1. Then you have a switching load. The way it is switched is it is connected in series with the MOSFET. And sorry, so this is a resistor right here. This is R2, and this is connected to ground. And this is triggered by a GPIO, by the MCU. And so when this turns on, you have the R2 connected in parallel to R1. You see the PWM is triggered out of, sorry, I hope you're not getting busy with this. Okay, so the PWM is coming out of pin 67 here, and it goes, and so the PWM, the one thing to keep in mind is the buck converter has a P-FET instead of an N-FET. So in the positive cycle of the buck, the transistor will be turned on when the signal is negative, and it will be turned off when the signal is positive. But for a better understanding, it's easier to generate